the disadvantages of lagging power factor, the causes of lagging power factor or low power factor, then how we can improve the lagging power factor. So these are all the things we are going to study today. If we have a better power factor, the machine can perform better. We'll see what is meant by power factor. Now we consider a resistive load. Now see, this is the voltage waveform, and this voltage waveform can be represented by a vector, and this is your current waveform. Now look at the starting point of voltage and the current. Both waveforms start at the same point, and they both reach the maximum point at the same instant. So you can say both waveforms are in phase. Both voltage and the current are in phase. There is no phase angle difference between voltage and the current. So in the case of resistive load, they are going together. Both voltage and the current start at the same point. Now the current waveform can be drawn in phase with voltage. This is a current waveform and this is the voltage waveform. They are in phase, they are going together. So in this case, there is no phase angle difference between voltage and the current. Phi is equal to 0. So what is cos phi? Cos phi is equal to 1 unity. Now we consider a purely inductive load. So this is our voltage waveform and this is our current waveform. Now we look at the starting point of voltage. So the voltage starts at this point, whereas the current starts at this point. So the current starts later when compared to voltage waveform. Current starts after 90 degrees, the voltage starts. So you can say the current lags behind the voltage by 90 degrees. Current is going behind the voltage. And suppose this is the voltage phasor. Then the current phasor can be, the current vector can be drawn like this, because current lags behind the voltage by 90 degrees. As you know, the vectors are rotating in the anti-clockwise direction. So the current is going behind the voltage by 90 degrees. So here phi is equal to 90 degree lagging. As the current lags behind the voltage, you can say phi equals 90 degree lagging. So cos phi is equal to 0 lagging. Now we consider a capacity load. This is our voltage waveform and this is our current waveform. If you look at these starting points, this is the starting point of voltage waveform. But what about the current? Current starts earlier. So you can say current is going in front of the voltage. So current leads the voltage waveform by 90 degrees because the current starts later. Current starts earlier. So current leads the voltage by 90 degrees, or you can say voltage lags the current waveform by 90 degrees. Voltage is going behind the current waveform, or the current is going in front of the voltage waveform. Suppose this is your voltage waveform, then this is the direction of current waveform. Current leads the voltage by 90 degrees. Current is going in front of the voltage vector. So here phi is equal to 90 degree leading. Current leads the voltage by 90 degrees. So what is the power factor? Cos phi is equal to 0 leading. Now we can consider a motor load. As you know, the motor winding consists of both resistance and inductance. So this is an RL type load. If it is purely resistive load, as you know, voltage and current are in phase. If it is purely inductive load, the current lags behind the voltage by 90 degrees. In this case, we have both resistance and inductance. Suppose this is your voltage. Now this is the current waveform here. So here the current starts at this point. This is the starting point of voltage. If you look at this picture, you can see the current starts some 60 degrees after the voltage waveform. So you can say this is your 30 degree, this is 60, this is 90. So you can say the current lags behind the voltage by 60 degrees. So phi equals 60 degree lagging. So in this case, cos phi is equal to cos 60. So this is the case of an RL load. So this is lagging type, current lags behind the voltage, and this lagging angle will be somewhere between 0 and 90, as you are having both resistance and inductance. Now we will see the power triangle. Suppose this is our apparent power, and this is at an angle of 5 degrees with respect to x-axis, and this apparent power can be resolved into two components. The horizontal component is called active power. So this is P equals VI cos phi. The vertical component is called the reactive power. It is VI sin phi. The unit of apparent power is volt amperes. The unit of active power is watts. Unit of reactive power is volt ampere reactive. So these are the three power terms usually we use with the power system. One is apparent power, volt amperes. The second one is active power, which is in watts. The third one is reactive power, which is in volt ampere reactive. If you draw a line here, these two lines are equal. So this is also equal to VI sin phi. Now you consider this triangle. Which are the sides of this triangle? The hypotenuse is VI. The other sides are VI cos phi and VI sin phi. This triangle can be redrawn here. What is the hypotenuse? It is VI. This is called apparent power. And this side is P equals VI cos phi. And this side is Q equals VI sin phi, and this is called the power triangle. So this is our power triangle because its three sides represents three different powers: apparent power, active power and reactive power. From this triangle you can write cos phi is equal to VI cos phi divided by VI. What is VI cos phi? This is active power. VI is apparent power. Actually, the total available power is VI. Out of this VI, a certain part is utilized. This is the useful power. Active power is the useful power. So this, what is this cos phi or the power factor? It tells you what factor of apparent power is utilized as an active power. So the power factor tells you what factor of apparent power can be utilized. It is P by S, active power divided by the reactive power. If you consider a motor, if it is an induction motor, it needs both active power and reactive power for its operation. When you give electrical power, it is converted into mechanical power. Actually, the active power is converted into mechanical power. But why we need the reactive power? It is to set up the magnetic field. So the reactive power sets up a platform called reactive power in which the energy conversion takes place. Now we'll look at this picture. What is meant by power factor? It tells you what factor of apparent power can be utilized. Now suppose this is the total voltamperes and this person has got some problem in his legs, so he cannot utilize his power as effectively as the second person. So I can say this is just like voltampere reactive, and this is his actual useful power. If there was no problem in his legs, he could have utilized his power more efficiently and more effectively. If there is no voltampere reactive, more amount of power can be utilized. Now we look at the second person. There is no voltampere reactive, so the complete VI will be utilized, or more amount of VI will be utilized as the active power. For example, suppose phi is equal to 0. So cos phi is equal to 1. In this case, there is no reactive power. Reactive power is equal to Vi sin phi. This is equal to 0. What is active power? P is equal to Vi cos phi. Cos phi is equal to 1. So P is same as Vi. What is Vi? This is my apparent power. So when the power factor is better, when you have high power factor, more amount of apparent power will be utilized as active power. In this case, the power factor is the highest value. Power factor equals 1. Now what is the active power? It is same as the apparent power. The complete apparent power is utilized as the active power. Now we will see some of the disadvantages of low power factor. As you know, this fan is an induction motor. Suppose for its operation, we need to give some 100 watts power. As you know, P is equal to Vi cos phi. Suppose its power rating is 100 watts. And you have some 25 volts. Suppose the power factor is unity. Now what is the current required? If the voltage is 25, you need to give 4 ampere current. The second case, you consider the same 25 volt with half the power factor. Power factor is low. Now what is the current required in order to get 100 watts power? You need to give 8 ampere current. So you can say when the power factor is reduced, you need to give more amount of current. So when you have low power factor, the current required is high. As you know, when the current increases, what happens to I square R loss? I square R loss also increases. So with the lagging power factor, the copper loss is very high. As you know, when the power factor is low, the current requirement is high. When the current is high, you need to have bigger conductor because the conductor has to carry higher amount of current. So the conductor size increases when the power factor is low. When the power factor reduces, as you know, the current increases. When the current increases, the resistive drop and inductive drop, IR and IXL, they both increases. Both IR and IXL increases. What is meant by regulation? Regulation means is the voltage drop divided by the rated voltage. So when IR and IXL increases, the regulation becomes poor. This is the voltage drop. Voltage drop due to resistance and inductive reactance. So the value of regulation increases. Value of regulation increases means it becomes poor, because we do not want higher regulation. We want to have minimum regulation. We want to have minimum drop. When the power factor is less, actually the handling capacity of our equipments will be reduced, because at low power factor certain amount of power will be used to meet reactive power. So only less amount of power will be available for the active power. So the handling capacity of the system will be reduced. Now we'll see the causes of low power factor. Most of the AC motors we use are induction motors. What is the motor used with the fan? This is induction motor. And in the water pumping system we use induction motors. In both AC and refrigerator we are using induction motor for the compressor. Then in mixer also we use induction motors. So all these induction motors are working at low power factor. The second cause for the lagging power factor is arc lamps and discharge lamps. With arc lamps and discharge lamps we will be using ballast, or we will be using chalk. Actually this is a coil. Why we use this ballast along with the discharge lamp and arc lamp? Because for the working of these lamps we need to give high voltage. For the production of high voltage we should use ballast or chalk. You have seen the chalk with the fluorescent lamp. So this chalk or this ballast will cause low power factor. And the third cause for the lagging power factor is the varying load in the power system. As you know, when the load changes, the voltage changes. So the voltage depends on the load. The voltage depends on load. At light load condition or at low load condition, the voltage is high. When this voltage is high, it causes high magnetization current. It causes high magnetization current in the transformers. So this magnetization currents will also cause low power factor.